For over 60 years, the entire digital world has been built on one fundamental idea. Move electrons around fast enough and you get computing. Every transistor in every chip you've ever used works the same way. Charge on, that's a 1. Charge off, that's a 0. Billions of times per second, every second, endlessly. It's elegant, it's proven, and it's running out of road. Here's the thing that people don't talk about enough. The problem isn't that we can't make transistors smaller anymore, though that's getting seriously hard. The real crisis is energy. When you shrink a transistor to the nanometer scale, it starts leaking current even when it's switched off. That leakage adds up. It adds up across billions of transistors, across billions of devices. And right now, data centers consume around 1 to 2% of global electricity, with AI workloads pushing that number higher every single year. The physics of silicon is becoming the enemy of the industry that built itself on silicon. Something has to give. So, what if we stopped moving electrons altogether? Sounds crazy? Well, what if instead of flipping charge, we flipped magnets? Electrons aren't just tiny particles with a charge. They are also a quantum property called spin, and spin has two states, up and down. Traditional electrons ignore that completely. Spintronics, or spin-based electronics, takes that ignored property and makes it the entire point. Instead of representing a bit as a charge present or charge absent, spintronic devices represent it as magnetic orientation. A magnetic moment pointing one way is a 0. Pointing the other way, that's a 1. The information lives in the physical orientation of the material itself, not in whether current is flowing. That is already being used today, and you've probably heard of MRAM, which stands for magnetoresistive random access memory. It stores data using magnetic tunnel junctions, thin layers of magnetic material sandwiching an insulating barrier. An electron tunneling through that barrier will do so more or less easily depending on whether the magnetic layers are aligned or not. That difference in resistance is how you read the bit. What comes next, and what most people don't realize is already in motion, is using the same principle not just for memory, but for logic, for actual computation. In September 2025, engineers at MIT published something that Forbes called one of the biggest tech breakthroughs of this year. They built a working magnetic transistor by replacing silicon in a transistor surface layer with a two-dimensional material called chromium sulfur bromide. That material is antiferromagnetic, means its magnetic moments alternate in opposing directions at the atomic level. What makes it remarkable, though, is that you can switch cleanly between two distinct magnetic states using an electric field, and that switch directly modifies the material's electronic properties. That's the key insight. The magnetism and the electronics aren't separate systems, they're the same system. MIT Associate Professor Luqiao Liu put it directly. Not only are these transistors switching on and off, they're also remembering information. That's a 3-in-1 action: switching, amplification, and built-in memory. In a conventional chip, the logic and memory are separate. Moving data between them accounts for a massive share of total power consumption. If the transistor itself can hold state, you've just cut a huge portion of the overhead at the architectural level. And unlike a lot of exotic 2D materials that degrade the moment they touch air, chromium sulfur bromide is air stable. That's not a minor detail, that's the difference between a lab curiosity and something that can actually be manufactured. Now, this isn't just academic. The big foundries are already in it. Samsung has developed an 8nm MRAM process and announced their embedded MRAM roadmap targets 5nm production by 2027. Their 8nm generation showed a 62.5 faster write speed and an 11.5% higher density than the previous 14nm generation. TSMC is developing MRAM as an embedded, non-volatile memory option for its advanced logic processes, including collaboration with research institutes to target automotive and AI edge applications. Intel, on the other hand, is exploring spintronic memory integration specifically for data center workloads where energy efficiency and data retention are critical. Intel and Georgia Tech researchers have already designed a 7nm SOT MRAM device together. GlobalFoundries and UMC are in the mix too. And then there's Everspin Technologies, which has been producing commercial MRAM for years, with IBM's next-generation flash core modules featuring Everspin 1GB STT MRAM. That's not speculative, that's a shipping product. The market research reflects it. The spintronic memory device fabrication market is projected to grow at 18% compound annual growth rate through 2030. That kind of number doesn't show up for technologies that are still purely theoretical. Now let's be precise here, because the hype usually glosses over this. Magnetic chips are not going to replace your CPU at 5 GHz. Not soon, maybe not even in that specific role ever. Magnetic switching speeds are slower than the fastest silicon transistors operating at a high voltage. High performance, high clock speed compute is still silicon's game for the foreseeable future and probably will never be replaced. But look at where computing is actually growing. Edge AI inference, IoT sensors running on a coin battery for years at a time. Automotive electronics that need to survive extreme temperatures. Aerospace and defense hardware that needs to function in radiation environments. These are the domains where the non-volatile nature of magnetic storage becomes a genuine superpower. Non-volatile means the device retains its state without power. Silicon transistors forget everything the moment the power cuts. A magnetic device holds its last state indefinitely without consuming a single watt to maintain it. For a system that's mostly idle and occasionally wakes up to run a task, the standby leakage that's killing silicon is simply not a problem. Instant on with no reloading from slower memory tiers, no boot sequence, no wasted cycles, and in radiation-heavy environments, magnetic state is far more resilient than charge-based storage, which is why spintronics gets serious attention from aerospace and defense contractors. There's also a compute-in-memory angle that's becoming increasingly relevant for AI. Moving data from memory to a processor is arguably the single most energy-expensive operation in modern computing. A 2025 paper published in Nature Electronics described a fully parallel spintronic compute-in-memory chip for AI inference, described as lossless and capable of performing matrix operations directly in memory. If you care about the energy cost of running large models at the edge, then this is the architecture that makes it viable. Okay, now it's time to be fair to the full picture. Spintronic logic faces real obstacles, and dismissing them would be dishonest. Switching magnetic states reliably at the nanometer scale is, well, it's hard. There's a fundamental tension between stability and you want the bit to hold its state, and switchability, which is when you want to flip it quickly and with low energy. Pushing both at the same time is a materials engineering problem that hasn't been fully solved for logic application at scale. Integration with existing manufacturing infrastructure is the other wall. Fabs are optimized around CMOS processes, introducing new magnetic materials, new deposition techniques, new annealing steps. It all adds cost and complexity. The good news is that magnetic layers can be deposited on top of silicon substrates without dismantling the existing fab infrastructure entirely. It's evolutionary, and it's not a ground-up rebuild, but it still requires significant development investment, and the industry has a strong incumbent bias towards what already works. Now, silicon isn't dying in 5 years. That's not what's happening. What's happening is a quiet bifurcation of computing hardware. High speed, high power tasks stay on silicon. Low power, always on memory adjacent and AI inference workloads shift to hybrid or fully magnetic architectures. The two coexist. Magnetic logic runs on silicon substrates. MRAM replaces SRAM and flash in embedded applications. Magnetic transistors eventually show up in chips that need to do 3 things at once, where silicon only does one. The most exciting version of this future is the one MIT pointed towards in September 2025, a transistor that switches amplifies, and remembers, built from a material that's stable, manufacturable, and physically smaller than what silicon can achieve at comparable power envelopes. That is a genuine shift in what the transistor even means. Not an incremental improvement, a new operating principle baked into the device itself. The energy problem is driving all of this. Power, not transistor count, is the primary constraint in computing now. That's the shift that changes the calculus for spintronics from interesting research to necessary engineering. When electricity bills and thermal limits become the bottleneck rather than transistor density, the technology that wins is the one that does more with less energy. And right now, magnets are looking like the best answer for a very large slice of the problem. So the question I'll leave you with is, if the entire AI build-out is running into a wall of power consumption and the best near-term answer comes from flipping magnetic moments instead of pushing electrons around, how long before everyone else figures out what the labs already know? Let me know what you think in the comments.